we will go back to where we were yesterday then. So we had ended, I was showing you an example of how to do the hypothesis test if you wanted to do it for tests about averages or means. We actually did 2 examples yesterday, I think, but this was the last one we got through. So the idea was we had this hypothesis test. We were trying to see if we could prove that the mean exceeds some value, which was the old average. So this is considered a one-tailed test, like a one-sided test. We only care if it gets too big. But because we're doing tests about means, we have to use the t-table to get our information off of. So we have to use our degrees of freedom in the alpha level. And on a 2-sided test, right, our rejection region is just one tail. And so we don't split our alpha level in half on a one-sided test. We just keep it as it is, and that's the column you go down the t-table and you intersect it with degrees of freedom row. That's where we came up with this critical value, right? Then you get your test statistic. It's just like calculating the z-score. It's just that it's actually a t-value now because you have an estimate of the standard deviation. But the way you make your decision is exactly the same. You take that test statistic and you see if it went beyond your critical value and out into the rejection region of the tail. And in this case, it did. And what it's saying is, what we're saying is that if the null hypothesis were true, then what we saw, our sample average, would be like 2.6 standard deviations above what we would have expected to see. So then that's pretty far from what they're claiming, basically. And because it's so far from what they're claiming, then that's good evidence that their claim is probably false, so we should reject the null hypothesis. So it looks like the mean price is high. Okay. But what we also talked about yesterday is you can go above and beyond just making your decision. You can actually sort of quantify your certainty with the p-value. And so if you can do a p-value on a t-test, you just have to be a little bit more careful, and it's not as precise. You just take your test statistic to whatever degrees of freedom row you're working on, and then you find out where is it bounded by. So you find the t-values in that row that bound your test statistic, and then the columns tell you where your p-value is. And so in this case, that one was somewhere between 1% and 0.5%. And we don't know exactly what the p-value is, but that's okay. We don't need to know exactly what it is. We at least know it's very small, because a p-value less than 1% is pretty conclusive at that point. That's really strong evidence. Yeah? Okay. And that's why, and the reason you do it is, the reason that we give the p-value is like, that helps people understand how certain you are. So like in this example, we're declaring that prices have gone up, and with a p-value of less than 1%, that tells people that we made our decision with a lot of certainty. And we can be pretty confident that that was the right choice. Okay? All right. Small p-values are good when you're trying to prove the alternative. All right. So I think I have another one. I don't need actually that slide. That's what we just did. But here's another example. So I'll let you read it first, and then we'll talk through it. Okay, so you get the main gist of it, right? The point is that the machine's supposed to be doing one thing, and you should periodically check it to make sure it's actually doing what it's supposed to do, but you can't possibly measure every single bottle, and so you just pick a few that you're going to do quality assurance on so that you can measure them more precisely and see if it's actually performing the way it's supposed to. So in this case, he pulls off 25 bottles, and the decision should be, okay, well, should the manager be concerned? All right, and let's just do this, I don't know, let's do this at the alpha, we can do it at the alpha 0.05 level, say. Okay. Or what, we used that one last time. Let's make it more interesting. Let's do like the 1% level or something. All right, so I should have probably included that in the problem, I forgot, so I don't know, maybe that's going to make things goofy, but we'll find out. But in reality, actually, we don't necessarily have to set an alpha level. We could just get a p-value and let the p-value make our decision for us, right? So anyways, we'll do it both ways. He gives his results back. That's the average. It's pretty close, but it's not 20. And the question is, should they be concerned? Because even if you were off by that much in the manufacturing process, that might be significant in the long run. But it matters what the standard deviation is, because there's going to be some variability in your fill rates. How would you frame this as a hypothesis test? So we need to get a null and alternative. So yeah, so the null would be that it's working. That's the way you should assume, until you can prove otherwise that it's not working. And you suggested a not equal to. Do you think that's the right? Why do you think it should be not equal to? You shoot it for 20. Now, why wouldn't you just do like a one-sided tail, like just greater than or just less than?
Because you would want to know both. You would want to know if you're spending too much by overfilling.
Exactly.
You also want to know if you're underfilling.
Yeah, it matters both ways, right? I care if it's overfilling or if it's underfilling, and so it's going to be this will be a good not equal to alternative. What are we talking about here? What's our parameter? We're talking about proportions or means? Everything here is in terms of means, so it would be our hypothesis has to be in terms of mu. And then we'll assume it's 20, but we'll see if we can prove that's not 20. Yeah? Okay, so when we go to get our critical value now, what do we have to consider? We're dealing with means, so what table should we be on? We should be on the T table. And the T table has degrees of freedom. So how many degrees of freedom do we have in this study? There's 24 degrees of freedom because there's 25 samples. Okay. What's our alpha level here? I set it as 0.01. In this case, it wasn't given in the problem. Now, yeah, that's the thing. Because, see, this one is a two-sided test. We care in both directions. So we need to split our alpha. We want to preserve our alpha level, but we want to split our rejection region into two pieces. So in this case, we do split it in half, like the confidence intervals. Okay. So in a two-sided test, you have to split your alpha level in half. The alpha level you split in half. The p-value you double. Yeah. Okay. Right, and the reason is because when you're talking about your alpha level is fixed. It's a fixed number, and you want to retain it when you split it across two tails, so you cut it in half. But your p-value comes from your test statistic and only using one tail, so you double it. Yeah. So you half your alpha level, but you double your p-value in a two-sided test. All right. So then what we're going to do is we'll go down this row. Oh, I'm sorry. This is the column. We'll go down that column until we hit the 24 degrees of freedom row. All right. So pull out your t-tables. If you don't have t-tables, I have some. You'll need, if you want to do the practice later anyway, you'll need to. So there's some. I'll just look at these up here if you want to come grab one. If you need some extras. All right, so you got your t-table. You go to the 0.005 column, go down to the 24 degrees of freedom row, and what value do you see there? 2.797. Perfect. So then that's your top value. But remember, it's two-sided. See, so the t-table just reads the positive side, the positive tail. And so then the cutoff on the other side would be the same, just the negative value. Okay. So then that's our critical value. And then these tails become our rejection region. All right. So what's next? We got to actually go get our test statistic. And so in this case, since we're dealing with means, it's a t-test. So we'll be using this formula. And so so then that's when you start pulling in the sample results. So this manager sampled 25 bottles and got us mean of 19.93. So that's the sample mean. We're comparing it to the claim, which should be 20 if the machine's working right. And then the standard deviation was 0.4. The sample size was 25. All right. And what do you get as that test statistic if you work this problem? Negative 0.875. Other people get that? Negative 0.875. You said the same thing, Tyler?
Yeah.
875. Now, this is where you have to be really careful. And I just mean careful like when you're taking the test. Not careful because this is tricky. It's just what happens is if you get a test statistic that's a decimal, a lot of people will want to stop and think that that's like a probability or something. But that's not a probability. That's actually like a t-score. Okay? It just happens to be a decimal value. Okay, so then that's our test statistic. So then what do we do with that value? We go, well, we can make our decision now without doing anything. What should be our decision here? Should we reject or not reject? We won't reject because you go back to the rejection region that you had set up, right? And you look at where your test statistic is. And it's not even close, right? Yeah, it's very close to the claim, basically. Yeah, it doesn't get anywhere near our rejection region because it's right there by, average. And so what's happening is in this case, what we saw is actually not very far from the claim, and so we shouldn't reject the claim because 19.93 seems to be close enough to 20 for us to accept that the truth could be 20. So then our decision would be, well, we would fail to reject. And so what are we really saying here? What's that? Yeah, so the really formal sort of interpretation would be talking about whether you have evidence in favor of the alternative. So we say there's not enough evidence to suggest the mean is anything other than 20. That's kind of like that's sort of like a double negative in your interpretation, right? You're saying there's not enough evidence that it's not working. So in reality, what are you really actually kind of deciding, basically? Yeah, I mean, a more informal is it looks like it's working, right? That's essentially what you're saying. Or as far as we know, it's working. I mean, we can never be for sure, right? We can never know for sure whether it's working, but looks like it probably is. Okay. What do you think? Questions on that one? Yeah.
The other way to find the rejection point is that once we get the negative 0.75, we take that to the p-table.
Yeah.
And then use the alternate.
Yeah. Yeah, I'm gonna do. Actually, we'll do that. But we'll do that just to see that you could do it that way. Because this whole critical value thing is always an option. It's not really necessary to do it with a hypothesis test, but you can do it this way and make the right choice. Okay. Any other questions about this approach, and then let's look at the P-value.
Can I ask a kind of off topic about the differential or degrees of freedom? Yeah. So why is that one less, and what is the degrees of freedom?
Well, what happens is it's because you're estimating two things, right? You're estimating in this test statistic, you're estimating a mean and a standard deviation. Okay, right? Okay, so but think about the standard deviation requires you to know the mean ahead of time, right? So if you told me the mean and you told me the standard deviation, and then you told me what 24 of the 25 observations were, I could actually back solve for the 25th observation. So what happens is, once you know one of these statistics, like once you know since these are related to each other, then you don't actually have like all 25 people aren't really random variables, because once you tell me what 24 of them are, the 25th value is fixed. And so then that's why we say it has 24 degrees of freedom. And it's because we're estimating two things. So it knocks out one one person's not really random in a sense, because I could hide them from you and you could still figure out who they were from the other 24. That's why it's called 24 degrees of freedom. Yeah. Any other questions? That is a little off topic, but it's interesting to know. Yeah. Okay, so then this was the critical value approach. We could go and we could approximate the p-value though. And so if you do that, remember, well, how do you do that? Where do you go to? You go to your 24 degrees of freedom row, right? Because that's the only place you can. The t-table is complicated in a sense, but it's also nice in a sense, because once you establish your degrees of freedom, it simplifies it to one row. You can only be working on one row in the table. All right. Well, so then you scroll across. What was our test statistic? It was negative 0.875. And in the t-table, though, since the t-table is only positive, we just use the absolute value of it, because it's not negative, so we have to use the absolute value. But the tails are the same on both sides, so it's fine. So you scroll across the 24 degrees of freedom, and you're looking for the numbers that bound your test statistic. So you'll hit really soon, what? You hit 0.857, and then it jumps up to 1.059. Yeah? And so then our test statistic, 0.875, is between these values. So then what do? Scroll back up the table and see what columns they came from. This was the 0.2, this was the 0.15. So then, well, our p-value, if it were a one-sided test, would be between those two. But in this case, what was true about this? Yeah, we had a not equal. Yeah, we can already make our decision now, even if it were a one-sided test. But since it's a not equal to alternative, you really are supposed to double your p-value. Sorry, that got messy, but so then actually our p-value here would actually be between 30 and 40%. That's a really high p-value. I don't know what happened there either. Yours. So that would be our p-value is somewhere between 30 and 40%, which is a very high p-value. And so you should definitely, it doesn't actually matter what your alpha level here is, because you just know, you would never use an alpha level that high. So, yeah.
Where is the 1.059 from?
It's on a table. So these values are these values are inside. Yeah, we can table it in. Yeah, these values are inside the table on the 24 degree row. So you're going into that row that represents your degrees of freedom, and you're trying to find out where on the spectrum from here to here does our test statistic lie. That's what you're doing. And you notice in the t-table actually reads the probabilities in its biggest to smallest, but that's because as you go across the table, you're going further out into the tail. So the probability of the tail is getting smaller as you push out. Yeah. Anything else? Any other questions about how to get those values? The key is just to remember that the not equal to alternative is the tricky one, because you have to you half your alpha level, but you double your p-value in a two-sided test. Yeah.
Can you tell us again what does a 30 to 40 p-value mean?
It means that if you reject the claim, then you have somewhere between like a 30 and 40% chance of making a type 1 error, basically. And so it's saying that you probably shouldn't reject because there's a high probability that the null is true. Yeah. So, because I said yesterday, because yeah, so the p-value is sort of a measure of how likely the null is. So the higher that p-value gets, the more likely the null hypothesis is. And so you should accept it with higher probabilities.
So if the p-value is really low, wouldn't that could tell you the opposite? That
Exactly.
That type 2 error is more likely to occur?
Well, not exactly. No, because remember, the alpha level is only controlling your type 1 error. So you all of your a type 2 error is harder to quantify because it's the probability of accepting the null when you shouldn't. But if the null is not true, then we don't know what the truth is. And so it's hard to quantify that probability more, because a type 1 error is easier to quantify because we're working under the assumption that the null hypothesis is true. So if you assume the null is true, that creates the normal distribution for the test, and then you work on that normal distribution. But a type 2 is a lot harder to quantify. Dealing with type 2 errors is much more difficult.
So when you were saying that you decrease type 1, type 2 increases,
yeah,
that's more so for like messy like things like torts.
Well, yeah, and it's it gives you a justification for what alpha level to pick. Because see, what it does is saying like, okay, I don't have as much control over my type 1 error as my type 2 error as I'd like, but let's say I really don't want to do that. So one way I could help myself out is I could lower my type 2 error rate by letting my alpha level go up. And so maybe I bump up my alpha level higher to 10%. And so what I'm doing is I'm sort of artificially I'm lowering this type 2 error. Even though I don't know how much I'm lowering it, I know that I'm lowering it. So I let my alpha level go higher. But on the other side, you might say, so then up there you might say, okay, I don't care if my p-value is 10%, because I really don't want this type 2 error, you know. But then sometimes it's the other way, my type 1's way worse, so you say, no, I want my alpha level really low.
So that's why you have us picking which one's worse, because you want to know
something to consider.
That when you're picking the p-value.
Yeah, exactly. You want to know alpha level. You want to think about the types of errors when you're setting that alpha level. Yeah, exactly. So while we're not going to spend a lot of time talking about type 2 error rates, that's still important because it controls your alpha level selection.
By chance, do you still have that slide where you have the significance of the p-value? Anywhere like the p-value is
Yeah. Yeah, this might have been the one I wrote down in my last class, but it's the same as this is the one right here.
Yeah, that's
yeah. Yeah, exactly. So the p-value is on a spectrum. And so you can say that, you know, in our case, we have a high p-value, so that's pretty much no evidence in favor of the alternative. So it works from here to here. And what you're doing is, as you move from here to here, you're decreasing the probability of making a type 1 error.
So in theory, if we grab that p-value, stay in or reject them.
Yeah, exactly, right. Because see, you could have, even if we would have, let's say we wouldn't have calculated a critical value here, by the time, if you go straight to the p-value, if you go straight to this p-value, you can already know what your choice is going to be. That p-value is so high, you should never reject. You know, because the rule is that if the p-value is low, right? So, did I tell you that's what my student, right? The rule is right. So if your p-value is low, the null must go. That's what he remembered it as. You know, and so it's like as that p-value gets really small, then you can reject the null. But in this case, the p-value is giant. So because it's so high, we don't even really need an alpha level here. We can just say, nope, looks like the machine's fine.
And either way, we're gonna ask what the p-value is.
I mean, I typically ask you to calculate it, but you could still make the right choice without it. So that's the key. Okay. So we didn't need the p-value to make the right choice. The right choice is that the machine looks like it's working. But you know, yeah. Okay. More questions? Other questions about this? Okay. So I have some problems here. These are just the Module 9 practice problems, but since we had a little extra time, I thought I'd give you a chance to try these out. So if you want to stick around and work on them, that'd be good practice. The solutions are in Canvas stuff, so if you need to, if you want to look at those on your own as well. Yeah, we make sure that's
We still get 1 page notes on this test, right?
Yes. Yeah. Sheet of notes for this exam. And make sure that tonight you're looking at the practice test. So that if you have any questions, you can come tomorrow. And if you need more Z's or T's, there's a bunch down here.
Almost took yours. I'm sorry.
You will need both for the tests. These and T's. Yeah, except for, so the test is very similar to the practice test, except for it's not going to as heavily focus on those first 3 problems. It'll be a little more heavier focus on the last few, the confidence intervals and hypothesis tests. I might throw like one of those Z-table questions on there or something, but it's going to be mostly the last few. 4, 5, 6, and 7. Yeah, I would focus more on the. You should try the first ones, but study more on the second examples. Module 8 and 9 as well. The Module 8 and Module 9 practice.
Hey, I had a question.
Yeah.
Can you show me how to plug this in on the calculator?
Yeah, that one's, if you want to do it all at once, so you're going to have to use parentheses in your numerator. So go parentheses. You got 19.93. And then close your parentheses. And then go divided by, and then go parentheses. And then go 0.4 divided by, and then go square root. What happens if you go square root? No, wait. Why does it do that? Ooh, that's bad. Yours is interesting. Yours doesn't have the inline. So the way you're going to have to do it is you're going to have to record the numbers separately.
Okay.
So you have to do 19.93.
Yeah.
Minus 20. Hit enter. And then that's going to give you your numerator. And then you're going to have to do then go
Here?
Yeah, and then down here, what is the square root of the size is 20?
5, isn't it?
I think it was 25. Yeah.
0.08, I think.
Right. Yeah, so 25. The square root of 25, if you hit square root, I think just hit
this one?
Yeah. Right. So then it's like 0.4 over 5. So then you can get that. So you can do 0.4 divided by 5. And then that's the 0.08 he was talking about. And now you can do the division, 0.07 divided by 0.08. Yeah, and then that's how you get the. That's how you get the.
Okay.
See, I was having the same problem.
Yeah.
With the so you just do it in steps. If
You
can't,
can,
like,
yeah,
do
yeah.
the whole problem.
Right, then you just do the steps.
Okay.
Yeah.
Okay, because I was getting like
If you want,
22.75.
yeah, if you want to do it as whole, then you have to put it the numerator in parentheses, and so you go 19. So you have to do 0.93 minus 20. So that's your top, and then you also have to put your new denominator in parentheses.
Yeah.
So 0.4 divided by, and then you can put in the square root of. Just the square root of 25, but see, then you have to be careful because that parenthesis just closes the square root.
Yeah.
So you need another parenthesis to close that denominator.
Oh.
So it's just
So
a lot of parentheses.
Double parentheses.
Yeah, right. Mm-hmm.
Okay.
Otherwise, if you don't put your parentheses in quite the right place, everything gets really goofy.
That's
Your
right.
calculator reads it really literally, and so then it's like it'll turn back weird numbers.
Okay, yeah, because I was doing it 3 different ways and I still wasn't getting it.
Yeah, you gotta have parentheses around the numerator, and you have to have parentheses around the denominator.
Okay.
So for the exam, like, what is, like, what, I know it can be a little bit of like 1 to 7, 8 and 9, but what